All right, so last time we talked about the application layer. We talked about principles of network applications, web and HTTP, email, and SMTP IMAP protocols. So it is now a good time to talk about domain name system, DNS. So people have many identifiers like your social security number, name, passport number, etc. Internet host routers have, on the contrary, have an IP address, which is 32 bits used for addressing datagrams. And like, it is like the human readable name of the host. And in this case, the IP address, every host connected to the network with an IP address. So memorizing all of these IP addresses is not a good thing. And as I also mentioned, people also don't remember web pages of famous web pages. People don't try to, type in facebook.com. They just type Facebook. So after the Google search, they click on the Facebook. So how to map between IP address and name and vice versa. For this system, we have something called DNS, domain name system. So this is a distributed database implemented in hierarchy of many name servers. So this is also a good example, by the way. People always think that distributed systems were invented by Bitcoin, but before that we have many examples like DNS or BitTorrent and so on. So, when you need something distributed, you don't have to use a blockchain. Sometimes you have other solutions like distributed databases. So this is an application layer protocol. Host DNS servers communicate to resolve names. This is also address name translation. Note that this is a core internet function implemented as application layer protocol. So complexity at network's edge. This is the thing. So you can sometimes leave the work to different layers. And actually in the transport layer, we will also talk about it. We will give some examples where we take the work from other layers to application layer. So since our computers are fast now, we can always leave it to the to the edge. So DNS services and structure are as follows. This is a host name to IP address translation, host aliasing, canonical alias name. So this means that a web page might have more than 2 domains. Like, I don't know if this is the case, but if Facebook also buys facebook.net, regardless of which facebook.com or .net you click on, this is alias, so they have the same, IP address or so. Mail server aliasing, load distribution, replicated web servers, many IP addresses correspond to one name. So this is also the good thing. In Windows, you can also add command prompt, write ns lookup, and then write the domain name. Sometimes it will give you more than one IP address because some web servers have more than one IP address. And if you constantly, check this, you will realize that the order of those IP addresses are, changing. This is to, have a better load distribution. So whenever you ask the IP of a domain name, the domain name server gives you the answer, but not always giving the same IP address if there are more than one. They change the order, so this way they balance the load. So question, of course, why not centralize DNS? Just have a single lookup at a server. So just query the server and obtain the result. Also, you can keep it one in your maybe local servers or in your computer if these tables are not big. The problem is that if you do it centralized, it will cause a single point of failure, and this will cause a huge traffic. And if the database is in a different country or continent, then this will cause a slowdown for you because you're querying in a distant server. And also maintenance. This is also a problem. Think about it. Just in old times we had phone books where there were the names of everybody and the phone number of those people. So it never worked. You search it, found somebody, call them, and you realize that they moved to another place 5 years ago. So that now there are somebody else living in that place. So this is the same thing. IP addresses change, domain names change. So keeping them updated sometimes is a huge problem. Yes, the answer is doesn't scale. For instance, Comcast DNS servers alone has 600 billion DNS queries per day. And Akamai DNS servers, in this case, 2.2 tera DNS queries per day. So as you can see, these are huge numbers. Centralizing them causes a problem. So this is a very huge distributed database, billions of records. But records are really simple. They are not complicated records. So we want to handle trillions of queries per day. Many more reads than writes. This is important. For instance, if you create a web page and buy a domain name, you have to connect that domain name to the IP address. So actually, you do it once, maybe for your life for that web page. So writing it, rarely changes, because maybe at some other time you change your hosting and pay somebody else to have the hosting. But since that hosting servers have different IP address, then you update your IP for that domain name. So this is why you rarely write something new, but read most of the time. And since you change it, in this distributed database, everybody needs to hear it, right? In the past, this system was slower. For instance, when I changed my IP address for my web page, some part of the world observes it instantly, but for some others, it might take hours or days. But nowadays, thanks to better computing and better connection, this update takes really maybe minutes at most. But reading is really fast. So because we have to read it and visit the web page, so it has to be very fast. This is why performance matters. Almost every internet transaction interacts with DNS, so milliseconds count. Organizationally, physically decentralized, millions of different organizations responsible for their records. Bulletproof, we need reliability, security. And this is not easy. So there are some DNS attacks, actually, which we will be talking about. After we finish talking about layers and talk about cryptography, we will talk about also attack types. But you can guess what kind of things you can do, DNS spoofing and so on. All right, the idea is as follows. At the top, we have roots. These are root DNS servers, and they are divided into categories. For like commercial web pages, which we have domain names that end with .com, you have different DNS servers. For organizations, others, and for educationals, for universities, you have different DNS servers. And below that, here, for instance, we could have our university here, or we could have other DNS servers like Amazon.com here, and so on. So client wants IP address for Amazon.com. First approximation is as follows. Client queries the root server to find com DNS servers, goes here. And this com servers, go to Amazon DNS servers. So from here, they get the, IP address and send it back to the person who asked it. But most of the time, you rarely reach to the root DNS servers. This is what actually we are trying to say here. Official contact of last resort by name servers that cannot resolve name. Incredibly important internet function. Internet couldn't function without it. For the security, we have solutions like DNSSEC, which provides security like authentication and message integrity. And ICANN is the organization who manages these root DNS domains. Okay, it's a short for Internet Corporation for Assigned Names and Numbers. So there are 13 logical root name servers worldwide, each server replicated many times. For instance, around 200 servers in USA and so on. So this is also important. I mean, if you don't have these servers in the area you are living, it might sometimes take longer for you to get this DNS result. So top-level domain TLD servers are here. They are responsible for many, extensions like com, org, net, and so on. And also you have country-level domains. In Turkey, we have .com.tr. We don't have the tr directly at the end, but we have added it as another dot. Network solutions, authoritative registry for .com, .net, top-level domain servers. For education, we have .edu, like for our university. And authoritative DNS servers are here. Organizations own DNS servers providing authoritative hostname to IP mapping for organizations named host. Can be maintained by organization or service provider. So we can have this as local DNS name servers. When host makes DNS query, it is sent to its local DNS server, because most of the time you will find the answer there. Local DNS server returns reply answering from its local cache of the recent name to address translation pairs, possibly out of date. So this is actually what happens sometimes if that's IP address change. If you read it from the cache, you will be actually visiting the old version. So you have to, requery it and check if it is out of date and so on. Otherwise, in the answering, forwarding requests into DNS hierarchy for resolution. Each ISP has local DNS name servers to find yours. Yes, you can find your DNS name from this command. In Turkey, people are very familiar with this command. Local DNS server doesn't strictly belong to hierarchy. So this is actually, if you change your domain name source, for instance, if a web page is blocked in your country, that DNS queries will be, you will be blocked. But if you use another DNS server, people in Turkey memorize all of this, Google DNS and so on. This is why, you can visit a web page that is blocked in your country if you change this name servers. But of course, if all of those are blocked, then you can use VPN and so on, which again, people are very familiar. Although they don't know what it is, they are familiar how to use it and how it works. So local DNS server doesn't strictly belong to the hierarchy. So here's an example. This is the iterated query solution. So a web page at a host at university wants the IP address for another university in another country. So iterated query, contacted server replies with name of server to contact. So it is something like this. You ask a person and they say that I don't know the answer, but this person might have. Okay. So this is the iterated query. So you ask your local DNS server, assume that it is not in the cache. So it's asked to root DNS server, and DNS server replies that you should ask it to the top level domain DNS server. So you ask it, they reply you back to tell you which authoritative DNS server knows the answer. You go for them, and they have the IP address for this domain name, and they reply you back. So as you can see, there are many packages transferring here. These are all UDP packages, by the way. They are fast, but having like 7 steps here, you might think that it will cause some milliseconds, right? It will cause some slowdown. So instead of iterated query, you can do something else. Here at the 8th step, we obtain the answer. Now, what you can do is a recursive query. Of course, some domain name servers support it, some do not. But this puts the burden of name resolution on contacted name server. Heavy load at upper levels of hierarchy. The question is that. So because you ask your local DNS server, it asks the root DNS server, and DNS server now says that, okay, I don't know it, but this top level domain name knows the answer, so I will ask it myself. So this server asks it here. It goes back, again, 7 connections, but now it is balanced in the sense that not every query is done by your local DNS server. So of course, you can think that maybe we will be putting a heavy load at the root DNS server if everybody does this, okay? So this can be solved by catching DNS information. Once any name server learns mapping, it catches mapping and immediately returns a catch mapping in response to a query. Catching improves response time. Catch entries timeout disappear after some time, TTL. TLD servers typically catch in local name servers. Cache entries may be out of date. If named host changes IP address, may not be known internet-wide until all TTLs expire. Best offered name to address translation. So this is actually what I tried to explain. So in the past, when you updated your IP address for your web page, for instance, sometimes it takes for a few days for some people in different parts of the world to get the new IP address. Okay, For this reason, sometimes people actually leave the copy of their web page in the previous IP address for a few days so that everybody will be still seeing the new web page. But nowadays, these TTLs are not that long. So at most, after one day, all of the DNS servers will update it. Okay. So let's look at what kind of records actually these servers are recording. So distributed database storing resource records, shortened as RR. So RR format is just 4 values, so name, value, type, and TTL. If your type is A, then the name is host name, value is IP address. So as you can see, this is the basic type of records that you keep. So you map the IP address to host name. If it is NS, name is domain, like foo.com. Value is host name of authoritative name server for this domain. So in this case, you don't know the IP address of this web page, but you know which authoritative name server actually has the record for it. Type CNAME, this is for alias name for some canonical name. For instance, ibm.com is actually, server is.backup.ibm.com. So these are canonical names. So it is recorded in this kind of records. MX is used for mails. So value is name of SMTP mail server associated with the name. Okay, because if you provide both a web page and then maybe email service, you will be storing different values for your web page and also for SMTP mail servers, right? So we will be exchanging DNS messages, right? These are UDP packages actually. So DNS query and reply messages both have same format. Here is actually covers everything. Message header. It is 16 bits number for query. Reply to query uses the same number. Flags, query or reply, recursion desired, recursion is available, reply is authoritative, and so on. As you can see, recursion, most of the time you might prefer it, but it may not be supported. So this recursion available actually is that flag from their response. Name type fields for a query are in the questions. RRs in response to a query. So you ask it here, and in the answers, they will give you RRs, okay? Records for authoritative services are provided here. Additional helpful info that may be used also provided here, okay? So here's another example, new startup, Network Utopia. Register name networkutopia.com at DNS register, for example, network solutions. Provide names, IP addresses of authoritative name servers and primary and secondary. Register inserts NS errors into .com TLD server like this, okay? So this hosting in the NS record says that this authoritative server has the record. Also here, for that, you put the IP address here. Okay, as you can see, the format is this time A. The record type is A, and in this case, NS. So create authoritative server locally with IP address with this one. Type A record for this web page, type MX record for this, okay? So what can go wrong? You can have distributed denial of server attacks for this because you can bombard root servers with traffic. So not successful to date. I mean, in the past there were some examples, but they didn't work. People tried this kind of attacks because it is not that easy to, I mean, they had precautions for that. So they could easily filter the traffic and realize that these packets are actually trying to make an attack and you can drop them. So up to date, as far as I know, no root server attacks happened in this way. Local DNS servers catch IPs of TLD servers, allowing root server bypass. So this is actually why it doesn't work, because most of the time, instead of asking the root to learn the TLD, you already keep the TLD in your cache. So rarely you actually ask for a record for the root server. But this means that you can bombard TLD servers. So, and this is potentially more dangerous, but I mean, if you attack the root servers and if you succeed, this would affect a huge part of the work, right? But when you attack the TLD, again, it's a huge part, but compared to the root server, not that huge. Okay, so this is an important problem. Spoofing attacks intercept DNS queries, returning bogus replies. There are DNS cache poisoning is one of the examples. You'd actually here, you provide false records to DNS servers, convincing them that you have the IP address of a web page, which is actually wrong. But this way you can fool the DNS servers, and they would send traffic to you, although they shouldn't be sending the traffic to you. Okay, so DNSSEC is kind of a solution to this, which we'll cover after we talk about cryptography later. Yes, so these are the topics that we want to look at the application layer. If you are more interested, you can keep reading the slides of the book, which also talks about peer-to-peer applications, video streaming, and content distribution. Also an example of socket programming using the Python language, which I'm not going to cover because we are more interested in the security. So we have to look at the layers first, then talk about cryptography, and then we will talk about attacks and the solutions or security precautions that we can have at the end.